சார் நீங்க ஸ்டார்ட் பண்ணலாங்க சார் ஒரு 5 செகண்ட்ஸ்ல.
A very good afternoon, dear students, faculty members, the guest, our dear principal, Dean Sir, and Dean Sir KC at USA. So it's a great day for Department of Mechanical Engineering to have two eminent guests in the field of noise and vibration. So it's my great honor to welcome our principal sir to give a warm welcome address for this August gathering. Please, sir.
Thank you, sir. So the most respected, eminent resource persons of this live webinar series, Dr. Michael Brennan, Professor, Sao Paulo State University, Brazil, and Dr. Philip Joseph, Professor, Institute of Sound and Vibration Research, University of Southampton, UK. Respected Dean, Dr. K. Chandrasekharan, sir, from US, beloved HOD, faculty members, and my dear students. A very good afternoon to one and all, joining in this live webinar series arranged by Mechanical Engineering Department. First of all, I would like to thank and welcome our eminent resource persons from Brazil and UK, Dr. Michael Brennan and Dr. Philip Joseph, for accepting our invitation to conduct this webinar series for the benefit of our students and faculty members. Thank you, sir. Welcome you, sirs, Dr. Michael and Dr. Philip Joseph. I would like to thank Dr. K. Chandrasekharan, sir, Dean of RMK Engineering College, for identifying such a eminent resource persons from Brazil and UK to conduct this noise, vibration, and harshness live webinar series by Mechanical Engineering Department. I also thank HOD and faculty members of Mechanical Engineering Department for conducting series of webinars, so many webinars for the benefit of students, faculty members of RMK Engineering College, and also faculty members of other engineering colleges. My dear students, hope you and all of your family members are doing good and safe during this pandemic period. On behalf of our respected chairman, sir, members of the management, all the faculty members, and my own behalf, I once again wholeheartedly welcome Dr. Michael and Dr. Philip Joseph for accepting our invitation and conduct this webinar for the benefit of our students. My dear students, really, we never ever expected this type of situation in our lifetime. But to make use of this period, with the strong support of our management and with the support of eminent resource persons like Dr. Michael and Dr. Philip Joseph, we have been conducting webinars for the benefit of all of you. We have also started conducting academic webinars to give foundation with respect to your subjects. So please make use of this webinar and attend and learn to enrich your knowledge to come out with excellence. My dear students, so definitely this live webinar series arranged by Mechanical Engineering Department, 2 days webinar series. So tomorrow we will have another 2 resource persons to continue this webinar series. I once again thank the Mechanical Engineering Department, and please make use of this opportunity, learn the new things, technology with respect to noise, vibration, and harshness. Once again, I thank the Mechanical Engineering Department for providing this opportunity for the students. Thank you for the given opportunity. Welcome, Dr. Michael and Dr. Philip Joseph. Thank you.
Thank you, Principal Sir. So it's my great honor to introduce the chief guest of the first session, Dr. Michael Brennan, State University of Sao Paulo, Solitaria, Brazil. He is a former professor in engineering dynamics for ISVR, University of Southampton, 2002 to 2010. He worked in sound vibration from 1995 to 2010. In 2010, he joined UNESP, where he is currently a research professor. He has been working on fundamental and applied research related to vibration and acoustics since 1995, both in UK and in Brazil. His research has encompassed a wide range of areas, including vibration, control, vibroacoustics, and nonlinear dynamics. He has supervised more than 30 PhDs and students to successful completion and has published more than 200 peer-reviewed papers in international journals. So such an eminent person, Dr. Michael Brennan, is with us today. So we are proud of you, sir, to be online, to give a virtual seminar for our students. So to highlight it, our first year student is also with you. So they just for inspiration, we have made them to join. So definitely they will get inspired in the years to go. When they complete, definitely they will remember you, your ideas, and it will be coming out as projects and patent with your support and help. So similarly, I feel proud in introducing Dr. Philip Joseph, Institute of Sound and Vibration Research, University of Southampton. He is a professor of engineering acoustics at the ISVR at the University of Southampton. He has been working on fundamental and applied research related to a wide range of acoustic related phenomena, including underwater acoustics, active noise control, aeroacoustics, duct acoustics, and advanced measurement techniques. He has supervised more than 30 PhD students to successful completion and has published more than 100 peer-reviewed journals, international journals, and is the inventor of 8 patents. So proud of you, sir. So today we are very proud and honored to have you in this August gathering with the students. Really, we are honored. Again, along with the principal, I would like to thank you for accepting, sparing your time in the busy schedule and for the benefit of our students, especially for the RMK Engineering College. Thank you so much, sir. Both of you, thank you so much. Now the session starts. Thank you.
Okay, so is that over to me now?
Yes, sir.
Dr.
Okay.
Casey, sirs, welcome.
Audio. Yes, sir. Sorry. 1 minute, sir. 1 minute. So Dr. Casey, sir, is in US, so the time is not matching with him. So we requested him to be with us, with all of us. So he has made a point to be with us in the audio mode. So he has sent a message in audio mode. So now I request the Easwaran sir to play the audio for all of our students, faculty, and also the guest. Thank you.
Thank you, sir.
Good afternoon, my dear students. This gives me great pleasure to address you all through this virtual platform. Hope all of you are doing well. In India, the importance of the effects of noise and vibration in the design of products and services has been recognized only in recent decades. The early work on these came to be related to vehicle design, and the term NVH, noise, vibration, harshness, emerged as an important parameter in design. Yet the understanding of the subject and the facilities for developing practical knowledge have not progressed to the desired extent. With more and more focus on human comforts and with the move towards lighter materials, the relevance of knowledge in this area of design and development of new products have intensified. With our institution going autonomous, this subject is going to help us in trying to develop expertise in this area with a focus on employment and entrepreneurship. The basic idea of this webinar is to give an introduction to the subject to generate interest among the students. We have been fortunate to get the world-renowned experts in the related areas to provide you the glimpse. Our college had a long understanding with the Institute of Sound and Vibration Research, University of Southampton, UK. For over 20 years now, we have been organizing periodical short courses to industry participants in this area with resource persons from the Institute. The success of these programs can vouch for the importance of this subject in the industries. Dr. Michael Brennan, currently Professor, State University of Sao Paulo, Brazil, and Dr. Philip Joseph, Professor ISVR, had been very kind enough to visit RMKEC and conduct this program all these years. We are very grateful to them for accepting our invitation to address you all today. Their formal introductions will follow. You must consider yourself lucky to hear them. Tomorrow there will be a talk on the applications in automotive engineering by one of the very practical and knowledgeable engineer in this area, Dr. S. Manivasagam of Tata Technologies. He has been driving the vehicle development in Tata Technologies and has brought in extensive collaboration between institutions like Warwick University, Advanced Manufacturing Group, and the automotive majors in UK. I am sure he would be giving you an insight into applications and emerging opportunities. Siemens have been spearheading the testing and measurement facilities in collaboration with several giants in this area. Sri Kumarasamy will be able to show you how testing and evaluation is done and the tools available. He comes with vast experience in this area. I express our sincere thanks to Dr. Manivasagam and Sri Kumarasamy for their acceptance and for joining us. I am sure this webinar series will motivate some of you to acquire special knowledge in this area and to take up your project works to provide the needed knowledge. We are looking forward to creating a modern laboratory for noise and vibration studies in the coming year. I express my sincere appreciations and thanks to all of them, the people who helped us in organizing this webinar series. I wish you all good health and Godspeed in your studies. Take care and stay safe.
Thank you, sir.
Sir, now Dr. Michael, please start.
Okay, thank you very much. And I would like to thank the principal and the head of mechanical engineering, and of course, Professor Casey, who we know very well. It was very nice to hear his message again. We haven't spoken to him for some time. So this is going to be an interesting experience for me as well. This is the first webinar that I have given. And so it will be interesting to see how it goes. And it will be a learning experience for me as well as for you. So I'll now share my screen. And can I just check that you can see my screen, which says Introduction to Vibration Control? Hello?
We can't see it yet, Mike.
You can't, can you see it now? No?
Not yet.
Okay, let me share screen again.
Share screen, sir.
Yes, I'm trying to do that. Right. Who can share screen only? Oh.
It's in the bottom middle.
Yes, it's in. Alt S. Try that. Can you see yet? No? No?
No, not yet.
Sorry, I'm having some technical issues then.
The fourth button at the bottom. Fourth button.
Yes. Yeah, I am pressing it.
Then it will ask for window.
Share screen.
Then you, yeah.
Nothing yet?
Sir, is it iPad or?
No, it's PC.
And then you get a choice of applications to share. You've got that, have you?
Yes. And then it says advanced sharing options. Who can share? All panelists.
No.
No?
You click in the middle, sir. So you click in the middle, sir, not the up arrow. You click the share screen text. Hello.
Hello. Yes, it just comes up as Alt S.
You click it, sir.
I clicked it, but nothing seemed to happen. Anything?
Not yet.
Oh dear. Oh dear. It's the green one that says all share screen. Is that?
Yeah, it's the green one. Yeah.
All right, and then it says share. Can you see now?
Yeah.
Yes.
Okay. Good. I apologize for my inexperience of this. So this lecture is going to be about an introduction to vibration control, and what I hope to achieve in the next 50 minutes or so is really just to give you some ideas of the concepts that we use. There is a small amount of mathematics, but I've tried to keep that to an absolute minimum. So why do we study vibration control? Why is it important? And I think there are a few reasons for this, but I've just highlighted a few here. One is to improve comfort. And I think we've seen a lot of this over the last recent years. Our environment now is much more comfortable than it was several years ago because of new techniques and technologies. Reducing noise, of course, which is very important. Phil is going to talk quite a lot about this, but I suspect he's not going to talk a lot about vibration, but it goes without saying that if you reduce the vibration, you will only help to improve the acoustic environment. To reduce fatigue, of course, there are many examples in mechanical engineering where things have failed because of fatigue, aircraft, ships, bridges, and so on. And when this happens, the results are catastrophic generally. And finally, to improve the perceived quality of products. And this becomes increasingly important to countries like India, who wish to make products for overseas consumption. So what am I going to do today? I'm going to give an overview, a very brief overview of some basics, and then I'll talk about ways to reduce vibration, and I will give examples as I go along. So a vibration control problem can be split up into three parts, which you can see in this diagram here. There's the vibration source, there's the vibration transmission path, and there is the receiver. And of course, the aim is to reduce the vibration at the receiver. Now, the best solution is to control the vibration at source. But this is not always possible. And for many, many years, this was never even undertaken. It is, however, now become a target for the high-tech companies. For example, Rolls-Royce, the high-tech companies from Korea, and so on. they employ engineers now to get involved at the design stage to try to reduce the vibration at source. By far, the most popular method of controlling vibration is to control the transmission path. And you will all have seen examples of this, and I'll show you some in the coming slides. You could try to control vibration at the receiver. That is sometimes done. But what I'd like you to remember that in all of these things, in general, the only thing that you can do is to control the mass, the stiffness, and the damping, both the amount and the distribution of these three quantities. So the problem is quite easy to state, and in some sense, it's quite easy to state the solution. However, it's very difficult to know how to change the mass, how to change the stiffness, and how to change the damping, and more importantly, when to change them. So let me just start off with some basics. And the first thing I just want to start off with is a single degree of freedom system. Now, vibration engineers conceptualize almost all of our real-world mechanical systems in terms of three quantities: mass, stiffness, and damping. And of course, the real world doesn't look like this mass spring damper system here, but we can conceptualize it to comprise of these quantities. So I'm going to look at a really, really simple system here, just a single degree of freedom system. And we can write down the equation of motion here. You'll notice it's excited with a sine function here, but we find it convenient to use a complex notation here in terms of the excitation. So because the system is linear, it will respond with a given amplitude, and it will respond at the similar frequency to the excitation. So we can assume that the displacement has this form, and we take it from here and we pop it into x here. We differentiate this and pop it into the velocity here. Differentiate again, put it into the acceleration, and then out comes a frequency response function. So in putting this into this equation and then doing some cancellation, we move from time domain into the frequency domain. And you can see that there are these three quantities here: stiffness, mass, and damping. And then the only other factor that is in here is frequency. So this is a complex number. So this will have a modulus, and it will have a phase. And I'm not going to talk about the phase today. I'm just going to talk about the modulus. So if we take the modulus of this, we get this expression up here. And I just want to spend a few moments just looking at this expression, because this is really a simple analysis, but quite an important analysis. If we take this expression and we plot it as a function of frequency, we will get different curves like this, depending upon the amount of damping here in the system. So what I would like to do now is to look at frequency regimes. So let us first of all look at a low frequency regime. So let in fact omega go to 0. So omega goes to 0. This disappears. This disappears, and I'm just left with 1 over the square root of k squared, which is 1 over k. So we have this point here, which is clearly, this point here is defined by the stiffness. So the displacement at this point at 0 frequency is independent of the mass and the spring and the damping, and it's only dependent upon the stiffness. So let us now, so let's just look at that. So the low frequency region, omega tends to 0, and then it becomes 1 over k. And if you look along this line here, you see this is approximately flat here. If we now take what we call the resonance region, which is around here, we can see what happens in this region by setting this term here to 0. So when omega squared m is equal to k, so when this term is equal to 0, then I'm just left with 1 over omega c. So what you see here is that within this resonance region, the damping is the only quantity which is important. And of course, finally, we move to the high frequency region. So we now let omega become very, very large. And now this term here dominates compared to the other terms. So we can neglect k and we can neglect this term. And we have a high frequency asymptote, which is this line here. And we're now in the mass control region. So what this really, really simple analysis has shown us is that with a simple system like this, there are frequency regions where different quantities control the vibration, control the level of vibration. And the vibration engineer, when he is faced with a vibration control problem, he has to determine which of these quantities to control. Do we make it stiffer? Do we make it lighter? Do we add more damping? And so you really need to know which region you are in. And I don't have time to go into talking about how we do that at the moment. I just want to highlight the fact that there are different parameters which control the vibration in different regions. So now let me look at the first measure of controlling vibration, and that is vibration isolation. And you will all be familiar with vibration isolation because you will have seen it in many different places. Here is a car, and littered in the car are vibration isolators. And the reason generally that you know that they are vibration isolators is because they will be made of rubber. And I'll talk a little bit more about that, but what in principle we do with vibration isolation is we interrupt this transmission path so that it's more difficult for the vibration to transmit through to the receiver. So here is a picture of a part of a car, and you will be familiar with the suspension system in a car, I'm sure, where you get these large coil springs. But what perhaps you're not so aware of is that all of these little joints here are rubber bushes. And these rubber bushes are all designed to act as vibration isolators. And so wherever you can in a mechanical system, it is always good to insert a resilient element between two stiff components in order to give some vibration isolation. Here is a picture of an engine with an engine mount. And on an engine, there may be 3 or 4 rubber mounts. These are actually quite sophisticated devices, even though they may not look it. They are designed to operate in a particular direction. Their stiffness is carefully tailored. And in some cases, these mounts have hydraulic elements incorporated in them. If we look at the exhaust system, so if you take a typical exhaust system, you will find that there is an element along the exhaust system which looks like this. And this here is designed to decouple the engine vibrations from the exhaust system. And it doesn't necessarily look like a vibration isolator, but it's designed to be flexible compared to the exhaust system either side. Also, the exhaust system has to be connected to the car, and it's connected to the car through a rubber isolator here. And the whole idea of this is to make sure that the engine and the exhaust system is not rigidly connected to the car. And in a sense, what you do with vibration isolation is you let the source vibrate. You do not try to stop the source from vibrating, but what you do is you try to stop that vibration being transmitted to an important part, which is, in this case, is the rest of the car. So I just want to go through a really brief example here. So there's a small amount of mathematics, but not very much. So on the left-hand side here, I'm illustrating a vibration isolation problem. So we have a source, and we model the source as a mass, and we have some excitation force here. And then we want to connect the source to a receiver, and in this case, we've made the receiving structure rigid, and we connect it through an isolator. And the isolator is modeled as a parallel combination of a spring and a viscous damper. And this isolator will transmit a force through to the receiving structure. Now, what is of interest from the vibration isolation point of view is the size of this force compared to the size of this force here. And if the transmitted force, Ft, is smaller than the excitation force, Fe, then we have some degree of isolation. If we were to connect the source directly to the receiver without using an isolator, then the transmitted force would be equal to the excitation force. There would be no isolation. So this is one problem. And the other problem is the reverse, if you like. So you can imagine, for example, a piece of equipment being suspended onto a host structure, and we suspend this through an isolator. And in this case, what we are interested in is the transmission of motion through this system. So we would like the transmitted displacement here, for example, to be smaller than this excitation displacement. So I'm going to look at this one here now in a little bit of detail. So we write down the equation of motion, which I'm sure many of you are familiar with. We assume harmonic excitation again, so Fe to the j omega t. And this will cause the source to vibrate. And then there will be forces transmitted through the stiffness here, the spring element, and through the damping element. So the force that goes through the spring element is K times X. X is this displacement. And the force that's transmitted through the damper is the velocity of this times the damping coefficient. So that turns out to be j omega x times c. Now, what is apparent, without doing any complicated analysis at all, is to note that for a given displacement x here, then at low frequencies, the force that comes to the receiver down here is mainly through the spring. But at high frequencies, because you have this omega term here, at high frequencies, then this force will become larger than this force. So the damper will act as a conduit for vibration, bypassing the spring. And this turns out to be slightly problematic. So if we combine equation 1 with equation 2, and we eliminate x, we can get what we call the transmissibility function, which is the transmitted force divided by the excitation force, which is given by this expression here. Then you can see, if you look carefully at this, you've got a j omega c here and a j omega c here. This term is exactly related to this one here, and this term is related to this one here. And it turns out that this term is good, this term is bad, okay? And we'll see why in a moment. So what we do is we plot that. So this is the plot of the transmissibility function, but rather than plotting the equation here, what we do is we non-dimensionalize this equation. We make a substitution for omega n is equal to the square root of k over m, and we make a substitution for the damping ratio instead of the damping coefficient. And what this does is it enables us to plot a kind of a universal graph, because we now plot the transmissibility as a function of non-dimensional frequency. And then you'll see that the only other parameter that we need to specify is the damping ratio. And so here are several graphs for different damping ratios. And it's plotted on a log axis. We tend to use log axes a lot in vibration. Now, what is clear that when we look at this is we see that there's two frequency regions, and below this particular frequency here, we don't get any isolation. In fact, we get amplification. So our isolator is behaving like an amplifier. And it's only when we get above this frequency here that we get isolation. All these lines here are below 1. And this point here is the resonance frequency. And I should perhaps just point out the difference between these lines. Okay? If you look at, for example, the blue line going towards the green line here, then we increase damping. Damping is very small, damping becomes larger. So when damping is small, we get a large response at the resonance frequency. And when we go to higher frequencies, that is beneficial. If we have a low response around the resonance frequency, we have a higher response above the resonance frequency. So the only thing that I want to say about this really is that this rather simple analysis describes what we see in general with vibration isolation. You cannot get isolation for all frequencies. You will get amplification, then you will get a resonance, and then above the resonance frequency, you will then get decoupling between the components, and you will start to get isolation. So you cannot get something for nothing with a passive vibration isolation system. Now, for a linear system, it turns out that this displacement transmissibility problem is exactly the same as the force excitation problem. For a nonlinear system, it's not the case, but for a linear system, it is. So here are just some little movies. So we've got a base excitation here, and you can see that there is no vibration isolation. The top moves exactly the same as the bottom. Then we hit the resonance frequency. So we get a large motion here. And this, in fact, is the penalty that we have to pay in order to get isolation above the resonance. So here you can see that the bass moves a lot, but the above the isolator does not move very much at all. If we excite the system with random excitation, you can see you get a little bit of motion here, but you still get quite good vibration isolation. And next time you're in a car, I suggest that you look at a car that is passing you, or a truck, and if you look at its wheel and the body of the car, you will see that it behaves exactly like this. So, some different isolator configurations. Generally speaking, we get our isolator from some kind of continuous system. And here is an element which is in compression, and the stiffness is given by E times A over L, the geometry. We don't very often see isolators like this. The reason we don't is because in order to get a soft spring, which would give us a low resonance frequency and a wide region of vibration isolation, it needs to be quite long. But so often you find that they're configured in shear so that you can get more compact isolators. And the shear stiffness is a function of the shear modulus, and the shear modulus is related to the Young's modulus through Poisson's ratio. So here are some isolator configurations. I've just taken these from the internet, and you'll see there's a huge variety of vibration isolators that you can buy. These are for hanging pipes, so these are kind of springs in the traditional sense. And these here tend to be used on board ships. So that's vibration isolation. That is one way of controlling vibration and disconnecting your source from your receiver. So let's turn now to a second way of controlling vibration, that using vibration absorbers. Again, if I take a car as an example, if you were to look inside a car, you would find there are many vibration absorbers. Here are, in fact, 7 of them. And there's one on the backrest, there's one on the steering wheel, there's some in the hydraulic system, there's some on brakes, they can be internal tubes, they can be torsional vibration absorbers and on the engine, and I'll talk about that a little bit more in detail. And then in some advanced cars, you will get some quite sophisticated active vibration absorbers. So what does it do, this device? So let me take a general structure here. We excite with a harmonic force, and we measure the harmonic response, and we form the frequency response function x divided by f. And it will typically look like this. In this particular example, this has 3 degrees of freedom, so there are 3 resonances. Then if we place a vibration absorber on there, which is simply a mass spring damper system, the effect that it has is this. And you can see what it does. It takes the peak and it puts a trough in that position there. It takes this peak and it moves it to the left a little bit, and it creates another resonance to the right. So previously we had 3 degrees of freedom. Now we've got 4 degrees of freedom because we've added 1. And that is the penalty for getting this huge reduction in vibration that's possible at this particular frequency. Now we can tune this depending upon the properties of the system. So we can make this a what they call a tuned vibration absorber, a lot of engineers will spend time designing these things to combat specific vibration problems. So let's have a look at how it works. Okay, so what we've got is a single degree of freedom system here. We've attached a vibration absorber. And we've got one resonance frequency here, this red one. And you can see that the two masses are moving in phase with each other. The red system here, the red spring and the damper, is in fact the vibration absorber. And over here, we've got another resonance frequency corresponding to this. And what is apparent here is that the masses are moving in antiphase with each other. And then we have this frequency in the middle corresponding to this trough, and we get the situation where the blue mass or the main system doesn't move at all. And it doesn't move because it's got two forces acting on it. It's got the main excitation force given by this black arrow, and it's got a force acting on it from the vibration absorber at this spring. And if you look very carefully, you will see that these forces are in antiphase. If you look at the motion of the mass and the motion of the arrow, you will see they're acting against each other. And if these are equal and opposite, then this will stop moving. And that's how it works. If we were to explore that a little bit more in terms of a frequency response function. So here's our system. Here's our main system, which will be typically a mode of a structure. Here's our vibration absorber. And we can plot the response of XS, this blue line here, as a function of frequency. And we can plot the motion of the absorber, which is this red line. And what is clear is that this particular point here, when this blue line is moving and it's changing its phase, I just pop back for a moment, you'll see here that the two masses are in phase, here the two masses are out of phase. So there has to be a phase shift occurring between this natural frequency and this natural frequency. So when the phase shift occurs, it moves from being negative to being positive. It has to pass through zero. And this zero here is what we're looking for in a vibration absorber. If we put some damping into the system now, we can no longer bring this mass here to rest. The reason we can't do that is because the force acting on the mass is no longer equal and opposite to the excitation force. The damper destroys that phase relationship. And so we will get a certain amount of motion of our main system. And typically, it will look like this green line here. So on this line, there's the original structure without the absorber. It's got no damping in it. Then we attach an absorber with no damping, and then we get our two resonances. And then we get this one here, which is the absorber attached with some damping. And in fact, this is what we're looking for. Often with a vibration absorber, we're trying to get a fairly smooth but low frequency response rather than these large peaks that you get. So damping, in fact, is quite a good thing to have. So different types of absorber, you'll find them. This is a simple one. Again, this is probably illustrative because you don't see this kind of thing often in practice. Okay, it's a mass on a stiffness and it's acting in tension and compression. This would tend to wobble around a little bit. This one may be better where this is now acting in shear. So this will be less wobbly than this one. And then finally, you get a kind of this device here, which is a flat device. So this here would be a beam which acts as the stiffness, and then this acts as the mass. So in fact, you get one vibration absorber here, and you also get another one here, but they act together to suppress the motion at this point. And I will show you an example of some of these in a moment. Yeah, the very first vibration absorber appeared in 1910, so slightly more than 100 years ago, and it was a device to stop the rocking motion of a ship. And you can see here there's water, and the water passes through this valve here, and as the water moves backwards and forwards, if it's tuned correctly, it can suppress the rolling motion of the ship. Here is a torsional vibration absorber, and most car engines have one of these fitted. And it's fitted at this end here, where you have a pulley. And if we look at the detail here, we see that the outer edge of the pulley is isolated from the inner edge of the pulley with an elastomer. So this will act like a mass. The outer part acts like a mass, acting back on the inner part of the pulley, which can suppress torsional motion of the crankshaft. Okay, here is one which is fitted to an exhaust system, and it simply looks like this. Okay, if you were to look at this and you were not familiar with vibration, you wouldn't have a clue what that is attached to that pipe. But what does give you the clue is stamped at the side as 95 hertz, which means that this here is tuned to a frequency of 95 hertz to suppress some motion of the exhaust system. And I'm guessing that this particular system had a problem with an exhaust system, and then this was fitted to try to solve the vibration problem. Okay, here's an example of a civil engineering. This is a bridge that was opened in London in 2000, and you can see when the people went onto the bridge started to wobble, and you can see it was quite bad. And what's kind of interesting is as the bridge vibrates more, the people all start to move in phase with each other. They actually cause the bridge to vibrate even more. So this is a bit like a positive feedback system, okay, but it doesn't act in a good sense. So what the designers had to do was they had to get some damping into this system without changing the design of the bridge. And they came up with a design where underneath of the bridge on all of these frames, they put a vibration absorber, which is like a mass and a spring. If you ever go to London and you cross this bridge, it goes from St. Paul's across the Thames to the Tate Gallery, the Tate Modern. And if you look underneath, you'll see these. They're not particularly attractive things, but they do the job. If you look at a set of pylons that carry electricity, you'll notice at the ends these funny things, these sausage-type devices. And they look like this. And these are vibration absorbers, and these are designed to operate in that way that I mentioned, to get some damping into these cables. And these are called stop bridge dampers. Finally, in terms of vibration absorbers, we can look at a building. Okay, this is the huge tower, Taipei 101 in Taiwan. And on top of this building is a huge ball. And this ball is a vibration absorber. And it's designed to control vibration. Let me just show you a movie, perhaps, if it works. So this is a different building. This is in Japan, but this is a building moving during an earthquake. It looks pretty frightening to me. Okay, so it moves like a cantilever beam, which is being excited at the base. So let me right, okay, and let me show you the movie of this Taiwan building. So this was taken, I think, in 2008. It's possible to go up and have a look at this building. And so you can see somebody there. And when these people were visiting, this started to spring into action. There was a large earthquake in Shenzhen in China at the time. Okay, and you can see this huge ball moving from side to side. So I think this would have been quite frightening for the visitors at that particular point. So what is also evident about this is the extremely low frequency vibration that they are trying to control. And it's because of its extremely low frequency that they need this huge mass. I think this is 800 tons, very large amounts. Okay, so let me just pick up. And again, right, and then down we go. So here's a very small vibration absorber. This is the last example. It's where we have an electrical resonator. So the electrical resonator is an inductor and a resistor, and we can connect to the main structure through a piezoelectric material. And the piezoelectric material acts as a capacitor. So because we have a capacitor and an inductor, we can get a resonance, and this can be used to put forces back onto the structure again, generated from the electrical system. And here's an example. Here's a baseball bat. Cricket bats, by the way, do the same thing as this. So this will have a mode of vibration, and the mode will look like this, the first mode. And if the ball hits at this point, then we do not create a lot of vibration. This is called the sweet spot. However, if the ball hits the end, this point here, then the bat will vibrate a lot, and you will get a sore hand, and the ball doesn't go very far. And I'm sure that quite a few of you will have experienced both of these situations in cricket. So if we were to look at the modes of the bat, so this is the first, the second, and the third, you can see that it's designed so that around this point here, there's a nodal point. So if the ball hits anywhere in this region, we're not going to excite this type of vibration. However, if the ball hits the end, then your hand is at this end, then there's a lot of vibration. So in terms of the baseball, people have designed a piezoelectric element. So they put a piezoelectric material into the body of the bat, and there's some electrics at the end, and this can add damping in the first and the second modes by quite a lot. So the difference in these levels represents the amount of damping that this can put into the system. Okay, so just onto the final topic briefly, Dan. This is not a large topic. This is vibration damping. This is the other way, another way of controlling vibration. And you will be familiar, I'm sure, with these spring damper systems, suspension units, which you get on motorbikes and cars and so on. But if you were to take up the carpets in a car, for example, you would see lots of material like this. And this is also damping material. So the automotive suspension system, if you were to look inside it, it consists of some a piston, and as this piston moves backwards and forwards, oil moves from side to side, and it is this that causes the viscous damping. If you look at the ends as well, you'll also see some rubber here. And this rubber, this is acting as an isolator, but there's also some damping within the rubber itself. And what damping does, if you were to imagine that you took the car and you perturbed it and then let it go, then if there was no damping in the system, then it would follow this black line. And then if you put some damping into the system, then and like this blue one here, then the vibration decays away very, very quickly. So that's what the effect of damping is on free vibration. In terms of force vibration, we saw right at the beginning that it controls vibration around the resonance frequency. So damping is only effective at controlling the response around resonance frequency. So you'll hear a lot of people talking about dampening down vibration. What they actually mean in many cases is reducing vibration, because damping is only a specific type of vibration control measure which acts around this frequency here. So by far the largest amount of damping that's put into structures is through added damping using viscoelastic materials. Again, we're looking at the inside of a car, and you'll see materials like this. And you'll notice that we have some materials like this, and these are gaskets. So nowadays, when people are designing a gasket, for example, for its primary purpose, which is to act as a sealant, then they will also build in damping properties to suppress vibration. And we use viscoelastic materials, and you'll be familiar with an elastic material where we have a stress-strain curve, which is a straight line. This is effectively a static loading of a system. And then if we've got some energy loss in our system, and we oscillate it slowly backwards and forwards, then what we will get is we'll get what we call this hysteresis loop. And the bigger the loop, the greater the energy that is lost. And that energy loss is related to damping. So the area of this loop here relates to the amount of damping in a system. And there are these viscoelastic materials come in all sorts of types of materials: plastics, polymers, rubber, etc. And they're actually really difficult to model. From a very simple point of view, we can model them in terms of a Young's modulus or a shear modulus. And you'll see this additional term here, eta. And this is related to some extent to the viscous damping ratio, zeta, that you see. But this is called the loss factor. Sometimes this is expanded out. So, for example, we get the real part of E and then the imaginary part of E. And this is sometimes called the storage modulus, and the imaginary part is called the loss modulus. And for the younger members of the class who've just been involved with learning about stress and strain, and Young's modulus and how they're related, then you will only probably have encountered the storage modulus. It's only when you start to look at dynamics that this loss modulus becomes important. And so we have this Young's modulus, the shear modulus, and the loss factor are important properties in terms of vibration, but they're complicated. They depend on frequency, they depend on temperature, they depend on the amplitude of the vibration, and they depend upon the preload. So what can look like a really simple thing, like some viscoelastic material, can behave in a very complicated way, and in order to be able to predict it, you need actually quite sophisticated tools. And you will know the frequency, the temperature dependence of these materials. You'll know, for example, if you take some rubber and it's very cold, it feels stiff, but as it becomes warmer, it appears softer. So the loss factor that you get is varies widely from material to material. So, and it's a very small number. If you look here, this is 1. This is a logarithmic scale. So this is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and 10 to the minus 4. So in this region down here are the metals, brass, steel, and so on. And then as we move up to 10 to the minus 1, we're looking at wood and asphalt and so on. And then rubbers and gels and so on occupy this region. And there are two fundamental mechanisms for putting a material onto structures. One is what we call unconstrained layer damping, where we simply layer on the material, and as the structure bends, you can see that the material stretches, and as it stretches, it will dissipate energy. Then we've got this other type where we put on a constraining layer. So this is a stiff layer. The effect that this has is it forces the material, the damping material, to strain, to shear, should I say. So it's the shear stiffness of the damping material which is important in this configuration. So in this configuration, in order to get large shear stresses in the material, we tend to have very thin layers, whereas with the other type of damping, the layers tend to be larger. Here's another type of damping, which is not really obvious. And this type of thing is used, not as you see here, but it is used in some things like hydraulic engine mounts. And it works on the following principle. If we have a volume here and a little hole at this point, and we move this plate backwards and forwards, then air will pass through the hole. And as it passes through the hole, you'll get viscous losses. And these viscous losses here give you the damping. But as this increases, as you go up in frequency, should I say, then what happens is this tries to move through here at a much faster rate, and the small amount of air that is in here becomes more and more difficult to move as you go up in frequency. And so the hole effectively seals at high frequency, which means you don't get any damping at high frequency. So this mechanism is a way of getting damping at low frequency, but not at high frequency. And along joints, for example, you can see it here. You get small amounts of air moving backwards and forwards, perhaps a little bit of friction as well, and all of this creates a little bit of damping into a structure. If you've got a bolted structure, then the amount of damping that you get is much greater than if you've got a welded structure, because you will get micro movements in here with bolted and riveted structures, whereas with welded structures, that tends not to be the case. Finally, here's an interesting application of just using a thin layer of air. So what we have here is the main plate, and then what we do is we attach a thin plate to the main plate, and it's loosely connected with these bolts, and in between is a really thin layer of air. This is microscopic. And then what happens is, as this vibrates, if the main plate and the attached plate have different thicknesses, then you get different wavelengths, different deformations at certain frequencies, and that causes the air in here to be pumped backwards and forwards, and that pumping of the air creates a damping effect. And this type of damping is used sometimes on ships when they want to damp a deck, and they can't use damping materials for that. Finally, here's a thing that we will remember from last year, perhaps, airplanes. And these all have, as you know, large engines on them. And these engines are very lightly damped. And it's very difficult to get some damping into this structure. And so what you find is that when the rotating shaft connects to the stationary casing, it connects through a ball or a roller bearing. And in between the ball bearing outer race here, which doesn't move, and the stationary casing, a really, really thin layer of oil is pumped into it. And this, as this vibrates, it wobbles around, squeezing this oil, which then creates some damping into the whole structure. And as far as I know, all aero engines have these types of dampers fitted. So that is it, I'm afraid. A very quick tour around different ways of controlling vibration. And I've basically highlighted 3 ways of doing it: vibration isolation, vibration absorbers, and vibration damping. And hopefully the examples that I've given will help you to visualize the main principles. So at that, I would like to stop. There are some books here which you can look at for further reading. So over to the chairman, please.
Thank you, Dr. Michael. So it was really an informative session. So any questions students or faculty can ask for 2 minutes, because already time is up for Dr. Philip. So please make it fast. If there is no question, if you want to ask at the end also, it's okay. Any question, faculty members or students?
Professor, can you elaborate on active observers? Active.
Yes. I can perhaps do that in a really simple way. Just go back here. So here, move this out of the way. So here is the vibration absorber, and essentially what happens with an active absorber, an actuator is put in here, which will apply forces to the mass and forces to the main system here. So this actuator can be piezoelectric or it can be electrodynamic. So rather than just getting passive forces acting on the system, you also get active forces acting on the system.
Okay. Thank you. Thank you, Professor.
Sir, good evening, sir.
Hello.
One of our students asked one question, simple question, sir. If suppose structure is something like cantilever beam, so how to determine the material damping in the beam-like structure, sir? damping. We know
Oh,
very well.
yes. Yes,
how
yes,
to-
I understand the problem.
Nice.
Let me just go back perhaps to a... Right, so if we were to look at this system here, so if we were to take a cantilever beam and we were to excite the cantilever beam, then at its first resonance, then it would have a response that may look like this line here. Right now, what you can do is you can measure how peaky that response is, and we call that's quantified by looking at what we call the bandwidth, and
Yes.
that bandwidth is directly related to the damping in the system. So as you see here, the wider the bandwidth, like this green line here, the greater the damping than if we have a blue line. We can also, so that's a frequency domain method. We can also do a time domain method. Let me just go to this graph here. You'll see that as the vibration decays away, so you could take your cantilever beam, take the end of it, perturb it, and let the cantilever vibration decay away freely, and we can measure how much that decays away. And by relating that decay of vibration, or by measuring it, we can relate it to the amount of damping in the structure.
Yes, sir. Thank you, sir. Thank you.
Okay, we stop here. Already we are 10 minutes, 15 minutes running short of time. So
Okay.
Thank you so much, Dr. Michael. So now the time is for Dr. Philip. Please, sir.
Okay, thank you.
Now, all right, so you start sharing your screen. Very good. Okay.
Yeah, I think that stops yours, I think.
Yeah.
Okay, but I need, okay. So can everybody see my screen okay?
Yes,
Yeah,
sir.
you're
yes,
on,
sir.
Phil.
Okay, thank you. Okay, well, like Mike, I'd like to thank the principal and head for inviting us. We've really valued our kind of long-term relationship with RMK Engineering College, and particular thanks to Professor Chandrakesharan, who we've known for many years, has become a good friend. So it's a real pleasure to be here. So in the next 50 minutes, an hour, I'd just like to give kind of an overview about acoustics and how to control sound, acoustics and noise control. So roughly the first half of my talk will be talking about the basic concepts of sound, acoustics, and then the remaining time we'll be talking about the basic principles of how to reduce that sound. Now, many of you will have studied vibrations in other subjects in mechanical engineering courses, but far fewer of you will have studied acoustics. So what I want to do, as I say, in the first 20 minutes is just to give you an overview of what sound is and how we kind of quantify it, some of the basic principles of sound propagation, and then go on to look at how we can control it. So let's start off with some kind of definition.
1 minute, sir. Dr. Philip, one humble request. So all the students are in undergraduate. So I request you to kindly not to go into deeper details, because they may not be in a situation to understand.
No, this is not detailed at all. This is very
okay. Thank you so much.
Very basic concepts.
Thank you so much, sir. Thank you.
You're welcome. You're welcome. But I think it's important to understand these basic concepts
Thank you, sir.
In order to understand how to control sound. So let's start off with some very simple definition. So what do we mean by sound? Now, sound is the pressure fluctuation, audible air vibrations that you can hear Okay, and your ear is sensitive to sound in the frequency range between about 20 hertz to about 20 kilohertz. Now, obviously, as you get older, the range of frequencies that you can hear gets lower and lower and lower. But if for a young, healthy adult, you should be able to hear frequencies in the range 20 hertz to about 20 kilohertz. Now, below 20 kilohertz, we call that infrasound, and above 20 kilohertz, we call that kind of ultrasound. And you're familiar with some of the applications of ultrasound for medical imaging, for example. Now, noise is exactly the same thing as sound, except we use the term noise to refer to unwanted sound. And as we know that a noise rather, can be disturbing, it can be annoying. And noise is actually very difficult to quantify because it's highly subjective. Now, some of the music that young people like to listen to may be regarded as noise by the older generation. So this is why quantifying noise can be really difficult sometimes, because it's highly subjective. And this is the real problem that people have in the automotive industry, because people are working very hard now, not just to make the car sound quiet, and that's actually relatively easy to do these days, but it's trying to make the car sound right, to give it a good quality, and that's what we refer to as harshness. Okay. Now, I'm not gonna say too much about kind of harshness in this talk. And acoustics really is just the study of sound. So before we kind of talk about what sound actually is, let's just think about what it kind of is in a very general sense. Now sound is a very small time varying fluctuation of the density. Now we know that if there is no sound, the ambient density in space is about 1.2 kilograms per cubic meter. And when you make sound, there's a very, very tiny perturbation of that density. Equally, sound can be thought of as a fluctuating pressure. Now, ambient pressure, atmospheric pressure, is about 10 to the 5 pascals. Now, when you make sound, even very loud sound, what you actually do is perturbing that pressure by a very, very, very small amount. We'll talk about how those levels in a moment. But we usually measure sound pressure rather than density, because sound pressure is very easy to measure with a microphone. Most sound pressures are typically less than about 1 pascal. Oh, I think there's a baby. Okay. So sound is a wave phenomenon. So if you clap your hands, or if you make sounds, what you're doing is you're squashing the fluid. But that fluid doesn't like to be squashed. Okay, so it expands again, and it overshoots, and then it compresses again. And so a wave is set up which kind of propagates through the air at the sound speed, which is about 340 meters per second. So sound, like vibration, is a wave phenomenon. Okay. Now, Mike Brennan talked about waves on beams and plates. Now, these are transverse waves, and that means that the motion is 90 degrees to the direction of propagation. Whereas sound is a longitudinal motion, as we'll see in an animation in a moment. So with sound, the particle motion is in the same direction as propagation. And another important concept about waves is that you need to understand is that there is no transfer of mass. No transfer of mass with a sound wave. So if you generate a sound wave by making some noise, you generate a pressure fluctuation which propagates through space, but you are not transferring any matter. And this next animation hopefully will explain that more clearly. So this is a very, very simple example of kind of one-dimensional sound. So what I'm showing here is an infinite tube. It's got rigid walls, so there's no motion of the walls. Now what I'm doing now is I'm exciting that fluid with a piston. You can see that red kind of plain piston source. So what I'm doing is generating one-dimensional sound. So the acoustic pressure is only varying axially along that tube. It's not varying in the transverse direction. So as that piston moves in, you're compressing the fluid. And the reason you're doing that is because the fluid is compressible. You can squeeze a fluid. And if you want some evidence of that, if you take a bicycle pump And if you close the end and just push down on the top, you can squeeze that air. So the air has a stiffness, it has compressibility. Okay, but the reason the fluid doesn't get away very, very quickly is because it has inertia, it has mass as well. So what happens now when the piston moves in, you're compressing the fluid, and that compression of the fluid propagates down the tube at the speed of sound. But more fundamentally, in some ways, what is happening is that you're exciting small particles in the fluid. So if you can imagine a very, very small volume of fluid, and if you very, very small, so that it's much, much smaller than the wavelength, okay, but much, much larger than at the size of a molecule. And I've shown some of these in red. So can you see that the velocity of these little particles are moving at roughly the same velocity as the source, as the piston source? And then these little red particles are just moving back and forwards inside the flow. So there is no matter being transferred down the tube. These little particles are moving just back and forward inside the fluid. And roughly they have the same velocity of the source. And we call this the particle velocity. So we have two velocities in this problem. We have the speed with which the disturbance travels down the tube, and that's the speed of sound, about 340 meters per second. And then we have the speed of the particles, which is much, 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 much lower, typically at millimeters per second. Okay, so it's important to understand those two concepts. Now, I'm sure you're familiar with these equations. These equations apply in vibrations as well as sound. Now, in acoustics and in waves generally, we describe the frequency, which tells you how rapidly the sound varies with time. In particular, it's how rapidly a single frequency wave changes with time. And associated with that is a wavelength, and that's the distance between adjacent peaks or troughs. And I'm sure you've come across this expression before, and it's very easy to show that the wave speed is the frequency times the wavelength. And we can illustrate that very simple concept with these animations here. So these are two animations of the tube, and what we're seeing now is the two tubes excited at the same frequency, but in the example on the right, the wave speed, the sound speed, is much lower. So you can see that because the waves travel much slower, the wavelength is shorter. So this is another example of C equals F lambda. And another example of that is where you have the same wave speed. For example, it could be sound in air, but you have different frequencies. So the example on the right is a much higher frequency compared to the example on the left, and that generates a smaller kind of wavelength sound. So again, this is another example of C equals F lambda, a result which applies equally to vibrations as it does to acoustics. Another important quantity, which is valid in sound and vibration, is this idea of linear superposition. Now, most people instinctively understand the idea of linear superposition, but I think it's actually quite a subtle concept. And it's the idea that if you have two waves occurring simultaneously, then the resultant disturbance is simply the sum of the waves individually. And the reason this is true is because the governing equations which governs the propagation of sound are linear equations. And that means that if P1 is a solution of our wave equation and P2 is a solution of our wave equation, then P1 plus P2 is a solution of our wave equation. Now, this is only true because our equations are linear and because the amplitudes of the acoustic pressure are generally much, much smaller than, say, the ambient pressure. Now, at very much higher amplitudes, say inside a jet engine, for example, when the fluctuating compression can be easily as high as atmospheric pressure, these linear equations break down and linear superposition no longer applies. Now, what happens is if you have sound inside of a closed pipe. So here is a very, very simple example of a rigid walled pipe. And what we're showing is sound propagating inside that pipe. Now there's a wave propagating from left to right with an amplitude of A1, And that reflects from the end on the right with an amplitude of kind of A2. Now, because we have rigid walls at the end of the pipe, the velocity there is zero. The particle velocity is zero. And what we find in this example is that if you generate sound in a closed pipe like that, which has got a length of L, then you set up acoustic resonances. Now, Mike Brennan talked about the concept of resonance earlier in his talk on vibrations. And what we find in this case is that you have resonances occurring when you can fit an integer number of half wavelengths exactly inside the length of the pipe. So when you have half, 1, 1.5, 2, 2.5. So when you can fit exactly an integer number of half wavelengths inside the pipe, what happens is the sound bounces back and forward. It gets bigger and bigger and bigger and bigger. And as Mike Brennan explained earlier, if you want to control the sound at the resonance frequency, it's controlled by the damping. So nothing else will change, nothing else will affect it. You have to absorb the sound at the resonance kind of frequency. Okay, so from that condition, lambda equals 2L over N, you can calculate the resonance frequencies for those very simple cases, for these simple one-dimensional cases, as N times the speed of sound divided by 2L. Now here's a kind of interpretation of that. So you can think about these modes, or we sometimes call them standing waves for reasons I'll explain in a moment, as being the superposition of two propagating waves. So if you kind of look at the example on the right, okay, here. So this is an example of a standing wave or a mode. And if you can see the variation of the pressure with time, it looks like it's standing. Okay, so the nodes, okay, the positions of zero pressure and the maximum pressure don't change with time. Okay, it looks like it's a standing wave. And you can decompose that in terms of a propagating wave on the left and a propagating a wave in the middle. Okay, and we call that a standing wave. And you'll notice from the animation that the particle velocity at the edges are kind of zero. But what is interesting is that the pressure is a maximum, the acoustic pressure, the sound pressure is a maximum at those edges where the particle velocity is kind of zero. Now things get slightly more interesting when you have a closed open pipe. And this is sometimes called an organ pipe. So now what you have is you have a closed end on the left and an open end on the right. And so you have a system of waves going from left to right, and then you also have a reflection from the open end. Now, you may think that because it's open to the atmosphere, the sound will escape perfectly. That's not true, because there's a large change in impedance going from inside the pipe to outside the pipe, so sound will get reflected. And what you can show then is that you also have resonances in this condition, but now the resonances occur when you can fit an odd number of 1/4 wavelengths in a distance L prime. Okay. Now L prime is the effective length of the pipe. And the effective length of the pipe is the actual length of the pipe. If you can see this equation here, the effective length is the actual length L plus what we call an end correction. Now, maybe this will be clearer if I show these pictures of the modes on this slide here. So on the left, you can see the kind of mode-shaped functions on a closed pipe. There you can see you've got maximum pressure on the walls, and you've got maximum pressure but zero pressure gradient, which means you have zero velocity on the walls. So these first two cases are you've got a half wavelength, 1 wavelength, 1.5 wavelength resonances. But on the right, we have the mode-shaped functions for the closed open pipe. And can you see that we've got an effective length here where you still have zero velocity on the left, but you have zero pressure on the right. And that zero pressure occurs at L plus delta. And that delta is this end correction that we talked about related to the pipe radius. Okay, so these are some very, very simple examples of one-dimensional mode-shaped functions in a one-dimensional system. Now, obviously, the concept of modes applies in 2 dimensions and 3 dimensions. Here are some plots of some 2-dimensional modes, and these are standing waves or mode shape functions on a kind of membrane, which you can see are kind of clamped along the edges. And you also get 3-dimensional mode shape functions in a room, for example, or in a car. Now, the modal representation of sound is very, very important at fairly low frequencies, in the frequency range where you can fit, 3 or 4, 5, 6, 7, 8 acoustic wavelengths inside the space. Now, at much bigger spaces, the concept of modes is no longer interesting or important, and I'll explain that. Process a bit later on. So let's just look at the range of sound pressures that you can experience. Now, this is kind of very interesting, because what you will see is that the range of pressures, the acoustic pressures that you can encounter in everyday life is huge. Okay, so if you're a young, healthy adult person, then you will be able to hear sounds at about 20 micropascals. So if I played you that sound, you would say, oh, I can just hear that. Okay, but then if I go outside and rustle some leaves, the pressure there is about 10 to the minus 4 pascals. If you and I have a kind of a conversation, the pressure there is, the fluctuating pressure is about 0.01 pascals. Inside of a vehicle at idle, it's about 0.1 pascals. If then we're traveling at about 120 kilometers per hour, it's 1 pascals. But then at 20 pascals, you start to feel the sound physically inside your body. And then at 200 pascals, you will do some permanent damage to your hearing. So the interesting thing is that the range of pressures, the acoustic pressures in nature is huge. And if you look at this, it's about 7 or 8 orders of magnitude. So for this region, our perception of the sound is logarithmic. And for that reason, we don't measure sound generally in pascals, we measure it in decibels. So what we do is we collapse this range of pressures onto a logarithmic scale, and we turn that into a decibel. And I'm not going to say too much more about decibels in this lecture. So far we've talked about sound as being a kind of a fluctuating pressure, which can propagate as a wave through space. But in many ways, a more fundamental way of thinking about sound is of a form of energy. I mean, acoustics is a branch of physics, and physics is really understanding various forms of energy. So a much more fundamental way of thinking about sound is as a form of energy. And the important property about energy that pressure and density doesn't have is that it's a conserved quantity. You can't make energy go away. You can only change its forms. And what we do in noise control, as we'll see later on, is we try to convert acoustic energy into heat energy. We try to dissipate it. So there are 2 kind of very, very important quantities in energy quantities in acoustics that I want to talk about. One is sound power. And the sound power is a measure of how much acoustic energy a source produces every second. Okay, and we usually express that in terms of a decibel. So the sound power level is defined as 10 log 10 of the power of a source in watts, okay, divided by some reference power. And for reasons which I won't explain today, we use a reference power of about a pico watt. Okay. So the sound power level of a source is extremely important because it allows you to compare the source strengths of different sources. So if you have a big machine and a small machine, then how do you compare the outputs of those different machines? Now, you could measure the pressure, but that will change depending on the environment, and it will depend on where you measure it. Whereas the sound power is a single quantity which tells you about the total source strength. It tells you how much acoustic energy is radiated per second. But there's another concept which is very important in acoustics, and it's the idea of energy flow, and we measure that by the sound intensity. Okay. Now, the sound intensity is just the acoustic pressure multiplied by the particle velocity. Now, we talked about the particle velocity earlier, and the intensity tells you the rate of transfer of acoustic energy through your unit area in unit time. So if you like, it's a power flux, and it tells you about the flow of acoustic energy. And a very, very important equation that we use a lot in acoustics is this one here, which I'm showing with my mouse. And this says that for one-dimensional sound, like the one in the tube, the intensity, that's the flow of acoustic energy through unit area, unit time, is related to the mean square acoustic pressure divided by another important quantity in acoustics called rho c, or the impedance of the air. And that's the density times the speed of sound. Now, if you go on to study acoustics or noise control, you will see that this quantity of rho c is very, very important in acoustics. And it's really to do with the impedance that the wave sees as it propagates through space. Now, I don't have time to say too much more about the idea of impedance. So I'd just like to kind of finish off this basic survey of acoustics by talking about kind of three-dimensional sound. Now, most sound obviously is not one-dimensional in a tube, it's three-dimensional. So here is a very, very simple example of three-dimensional sound. Imagine you have a source of sound at very low frequency, where the source is much smaller rather than the acoustic wavelength. And we call that a kind of a compact source or a point source. And generally sources like that, they radiate equally in all directions. And we call that omnidirectional radiation. So here is a kind of an animation of that. We have a source in the center, and you can see these kind of spherical waves being radiated out. And the acoustic pressure will decay as the wave spreads out spherically. And in fact, you can show that the acoustic pressure decays as 1 over the radial distance from the center. And you can see as well that the particle velocity is getting weaker and weaker as it spreads out from the center. Okay, so lastly, so there's another very, very important result I just want to finish on. And this is the kind of, for that very simple spherical radiation case, the kind of relationship between the acoustic pressure, the intensity, and the power. Now, hopefully you can see that for the case where the radiation is equal in all directions, the intensity, which is the flow of energy through unit area and unit time, is simply the power, just divided by the surface area 4 pi r squared. Okay, and we've also just seen that the intensity for a one-dimensional sound is just the mean square pressure divided by rho c. And very, very simply, what this tells us is that the mean square pressure varies as 1 over the square of the distance from the center. And this is the well-known inverse square law for light and sound, and for lots of other kind of wave type systems. Okay, now what this means for us is every time we double the distance from 1 meter to 2 to 4 to 8, 16, 32, we're going to reduce that sound by 1 over a half squared, which corresponds to 6 decibels. Okay, so that's a very, very quick survey of some of the basic principles of sound. Now, I just want to move on now to the last half of my talk, looking at the principles of noise control. What are the main techniques that we use to reduce kind of sound? And what we're going to look at is we're going to look at the use of absorbing treatments in what we call Sabine spaces and non-Sabine spaces. And I'll make it clear what I mean by that in a moment. And another very effective technique for reducing sound is simply to block it using barriers. And I'm going to say a little bit about that. I'm going to talk about sound absorption. What are the parameters that are important for absorbing sound, dissipating sound energy into heat? And then I'll just finish off talking about sound transmission. What are the factors that control how effectively sound gets transmitted across barriers? Okay, so we've already talked about sound in very simple one-dimensional systems, and we saw that there's a system of modes, there's a series of acoustic modes. What I'm interested in with this problem now is the situation where we're in a large room, and what I mean by large is that all of the dimensions are much greater than the acoustic wavelength. And in that case, there are too many modes. It doesn't make any sense to talk about the sound in those large rooms in terms of individual modes. So what we're going to do instead is we're going to talk about sound as being a kind of a statistical thing. So we're not going to talk about exactly what the sound pressure is, but what it's most likely to be. Okay, we're going to look at the mean square or the average values. And for that, we use a very powerful technique using diffuse field theory. And what a diffuse field is, it's a sound field in which there's an equal probability of sound arriving from all directions. So if you have an observer in the middle of the sound field there's an equal probability of sound coming from all directions. And this is a very powerful assumption, because it allows you to make very fast and very accurate predictions about the sound pressure inside these kind of large rooms. And this is what I'm going to do now. So just like Mike, I've only got these one or two equations, but the reason for showing you these is that these are very powerful equations for arriving at very useful results. Now, what I'm going to do now, this is called the energy balance equation. So I'm going to introduce a sound source into my room, and then I'm going to look at where the energy goes. So if I have a sound source inside of a room, now where does the sound go? Now, the rate at which sound energy goes into my room, this is the power of the source. I'm calling this W. Now, the rate at which power goes in must equal the rate at which power is lost from the room plus the rate of change at which the energy changes inside the room. So the rate of energy in equals the rate of energy lost plus the time rate at which energy changes in the room. Now I'm going to go through this quite quickly. Now the rate of energy going in, that's just the power of the source. The rate at which energy is lost from the room, that is simply what we'll call the intensity. Now the mean square pressure divided by 4 rho C, that's the intensity. This is the rate of energy flow through unit area and unit time in the room. And so the rate of the energy lost is that intensity multiplied by the equivalent absorbing area. Now this is a very important idea in acoustics. It's replacing all the absorption in the room by an equivalent area that is perfectly absorbing, plus the time rate at which energy changes in the room. Now this expression in the square brackets, this is the total energy in the room, and d by d of t of that just tells you the time rate at which that total energy changes. So just to summarize that, so we have A, which is the equivalent absorbing area. That expression there is the sound intensity, and that expression there is the total density. Okay, so that's really all I wanted to say about that equation. A very important equation, but the reason for showing you that is that we can derive some very important results in acoustics. Okay, so the first solution I'm going to show you is the steady state solution. Now imagine you have a source of sound inside the room. Now when you turn it on, okay, the sound level increases, but then very quickly it reaches steady state. There's a time at which the sound pressure no longer changes. And so the time rate of change of energy is 0. So under those conditions, we have an exact balance between the rate of energy going in, that's the power of the source, and the rate at which energy is lost from the room. So we can equate these first two terms here. And this is an expression now for the mean square pressure inside of our room in terms of the power of our source and the absorbing area A, which you can quite easily measure. Okay, so that's the steady state solution. And then the other solution I want to look at is the transient solution. Okay, so now what I'm going to do is I'm going to turn my source off. So I have 0 on the left-hand side, and then I get this first order differential equation. I can solve it for the mean square pressure. And this tells me now that if I make some sound inside of a room and I stop it, okay, if I clap, this tells me that the pressure inside the room decays exponentially. Okay, and then what I can do is I can use this expression for the rate at which the pressure is decaying with time to derive something called the reverberation time. And the reverberation time is the time taken for the sound to decay by 60 decibels. Now, people working in acoustics use this result all of the time. And the reason this is so useful, because every room, could be a concert hall or a teaching room, has its own recommended range of reverberation times. So here are some reverberation times that is important to have. And you can see we have classrooms and boardrooms, lecture rooms, small theatres. And these have got to have reverberation times of about 1 second. Inside general use halls, community centres, gymnasiums, the reverberation time generally has to be a bit larger. But then if you want to, these are kind of Western concert halls. If you have organ music or choir music, large concert halls, then the reverberation time tends to be a bit larger. So these reverberation times are very, very important for designing optimal listening spaces. Okay. So the other thing I just wanted to talk about is that when you're listening to sound inside of a room, some of the sound that you hear is radiated directly to your ear, and we call that the direct sound, and the rest of the sound is radiated by reflections from the walls, and we call this the reverberant sound. Now I'll go through this quite quickly. So then we can modify our expression for the mean square pressure inside of our room in terms of the power. Now we're going to use this now to predict the reduction in sound level you get, okay, by changing the absorption. Okay, so we can use this expression and we can calculate the reduction in the sound pressure level in decibels. So let's just look at some examples. Imagine you have a room with an average absorption coefficient of 0.2, which is quite small, so that's quite a reverberant room. And now we're going to increase it to 0.7. Okay, so we're starting off with quite a small absorption. We increase it to 0.7, and then you get a reduction of nearly 10 decibels, which is a large reduction. But if your original absorption is higher, say 0.5, and then you reduce it to 0.7, your sound pressure level reduction is much smaller. So adding absorption into a room is only really useful when the original absorption is quite low. And you can use this diffuse field theory to calculate the sound pressure levels in quite complex spaces. Okay, so here is an example of trying to predict the sound pressure level in this factory. You can see there's a fan on the left and there's some various machines in there. And here is an attempt to predict the sound pressure level. And it matches generally quite well. I won't say too much about that because we're kind of running out of time, but you can look at that for yourself. I'll distribute these slides if anybody's interested. Here is an example of a very simple case where they took a room and they filled it with polystyrene blocks. So in this room, you can see it's completely empty, this first case. The second room is completely filled with blocks. In this third room, there's blocks in the first half and it's empty in the second half. In this last room, they put the blocks on the second half and left the first half empty. And you can see there's a prediction of the predicted variation in the sound with distance compared against measurement, and it matches extremely well. Okay? So it's a very kind of powerful technique. The second concept I want to talk about is the idea of barriers. Now it's pretty obvious that if you put a solid barrier between a source and a receiver, then you get some reduction in the sound. And there are two main mechanisms for that. One mechanism is that you kind of blocked you blocked the direct propagation of sound through the barriers. And can you see the example on the right? These are some commercially available materials you can buy to block the sound. The one on the left gives a 60 dB block of sound because it's very thick, very dense. The one on the right is very thin, gives you a 17 dB reduction in the sound. So there are two mechanisms. One is that sound is absorbed, and the other one is that sound now, to get to the receiver, has got to pass over the top of the barrier to get to the ground. Okay, so what I want to do now is just show some very kind of simple predictions of that. Okay, now I don't have time to go through that theory, but this is quite simple diffraction theory, and you can look at this for yourself if you're interested. I'm not going to say any more about it than that. So it's very simple theory, but I just want to show some of the predictions from that simple theory. Now what I'm showing here is a rigid screen. You can see it in that black line there, and I've got a wave coming from the top right to bottom left. You can see it propagating, And you can see three regions. You have this region, which I'm showing on my mouse here, which I hope you can see. So now you have the interference between the direct sound and the reflected sound. So this is like a standing wave in there. And then you have this second region now where the sound just continues. But then you have this interesting region. We call this diffraction zone, where the sound pressure is much weaker, because in order for sound to get into that region, it must diffract around it. There's no direct path. And there was some very, 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 very fundamental, very interesting theory done by Mercauer. And he looked at how effectively these screens block sound. And what he did was he did this theoretically. He took a screen here, and you can see a source on the left and an observer. And he showed that what is very important for predicting the loss of by the barrier is what's called the Fresnel number. Now, the Fresnel number is the difference in the actual path length, A plus B, minus the direct path length that would occur if the barrier wasn't there. So he defined this quantity delta, which is A plus B minus D, and he showed that it was delta compared to the acoustic wavelength that was important in predicting the transmission loss. So here is the figure from the original Mercauer paper in 1968. And this is the transmission loss in decibels plotted against this Fresnel number. And you can see this very nice kind of straight line. So what is important is that you need a big path length difference delta compared to the acoustic wavelength. So these barriers are most effective when you're very close to the barrier and at high frequency. Another concept that we use a lot in noise control is to absorb sound, as I've already said. And sound absorption is really a technique to convert acoustic energy into heat energy. And we'll see in a moment that you can do that very effectively using very lightweight, quite thin materials. And you can see here is a kind of a modern building. And can you see this sound absorbing panel on the top? And the nice thing about sound absorbing materials is that they are mostly air. Okay, so here is some examples of well-known sound absorbing materials. These are mineral walls or glass fibers. Okay, and so absorbing materials, they're used a lot to control airborne sound which propagates kind of through the air. And we quantify the performance by measuring the absorption coefficient. So it's defined in terms of energy. So the absorption coefficient is the ratio of the absorbed energy, actually intensity, to the incident energy. So an absorption coefficient of 1 means that all of the energy is absorbed into heat, or just absorbed. 0 means that none of it is absorbed. Now here are some very kind of famous graphs here done by a guy called Meckel in 1988. And what he did was to measure the absorption coefficient alpha in percentage against frequency for lots of different materials, lots of different rock wall type materials. And they all had a different density, rho, and they also had a different quantity called the flow resistance. And the flow resistance is just the change in pressure divided by the velocity. So if you try and force flow through a material, it generates a pressure loss. Okay, and we call that the flow resistance. And that's probably one of the most important quantities for deciding how effectively these materials absorb sound. Okay, so you can see you've got lots of materials, different density, different flow resistance. But what Meckel did, which is genius really, is that he replotted these figures, and he plotted it against the density times frequency divided by the flow resistance. And all of these curves collapse, we say. They all follow the same line. So these are very thick materials. I'm not talking about the effect of thickness just yet. These are very thick materials. So for these very thick materials, you get these universal graphs kind of shown. I'll go through this quickly because I'm kind of running out of time. And then Meckel also presented these very nice graphs of contours absorption coefficient plotted against flow resistance and frequency. And I'll you to kind of read these for yourself. But if you want to design materials for optimal absorption, okay, these graphs are kind of very useful. I'll talk about sound absorption, looking at the effect of thickness. Okay. other results that Mikhail derived. This is plotting the absorption coefficient now against flow resistance, multiplied the thickness L of the material divided by the speed of sound. And what he showed was that the optimal performance of these materials was when the flow resistance times the thickness of the material was 3 times rho C. Now, this is a very kind of famous result that people working in acoustics all the time. So if you want to design optimal absorption and you have a finite thickness L, then you should arrange for its flow resistance multiplied by its thickness to be 3 times kind of rho C. Okay, just finishing off with some kind of practical sound absorption materials. So if you just had just some kind of porous material, then the absorption coefficient would look like this, alpha. So you can see that it's not very effective at low frequency, but it approaches 1 at high frequencies. But if you want to improve the low frequency performance, what you can do is you can put a perforated sheet. And people do this all the time. They add a perforated sheet to the sound absorbing material. And what that does is the sound absorbing material acts like a stiffness. The perforated sheet acts like a mass. And so you have a mass acting against the stiffness. This creates a resonance condition similar to what Mike Brennan described earlier. And so you get maximum absorption at these kind of resonance frequencies. If the frequency of maximum performance down to lower frequency, but you reduce the high frequency performance. Okay. So I just want to finish off the last five minutes or so talking about another important concept to do with sound transmission. Now, when we use these barriers or screens, if we send sound through it, some of that sound is transmitted and some of that sound is reflected. Now, what controls how effectively sound is transmitted? Now, here we have a screen. It's a plate or a panel. It's got a mass per unit area of mu. We have sound coming from the left. Some of that sound is reflected and some of that sound is transmitted. Now, what controls the transmission factor, the transmission coefficient of that material? So I'll go through this quite quickly and just show you the result. Now what I'm going to show you is the transmission loss in decibels versus frequency. Okay, and this is a very kind of well-known result in vibroacoustics. So now what I'm showing you is the transmission loss. This is kind of the ratio of the absorbed energy to the incident energy. Sorry, the transmitted energy to the incident energy, plotted against frequency. And let's look at that figure. So at very low frequency, as Mike Brennan explained, below the first panel resonance, the resonance frequency, the dynamics is controlled by the stiffness. So you can see that the transmission loss is quite high, but as you increase that frequency, oh, there's some strange noises going on. You hit that panel resonances, first panel resonance, and so the sound is transmitted much more effectively. So you get a transmission loss. And then above that frequency, I mean, as Mike Brennan explained, the dynamics is controlled by the mass. And then something very interesting happens, that as you increase the frequency, all of the transmission loss in this large frequency range here is controlled by the mass. And we call this the mass law. So the factor which controls how effectively panels and screen block sound is the mass. Okay, and it turns out that automotive panels, for example, their transmission loss is controlled by the mass over most of the frequency range. But then you increase the frequency still further, and then you see another dip in the transmission loss. Now at that frequency, we call this the coincidence region, because now there's a match between the acoustic wavelength over the surface and then the bending wavelength. So that because of that match condition, then sound is transmitted very effectively through the other side. But then as you increase the frequency still further, then a lot of that sound gets dissipated as heat. And now the transmission loss is controlled by the damping at very high frequency. So this is a very, very important curve for determining the important frequency ranges of a transmission loss through a panel. Okay, so how can we improve on this? So I'm nearly coming to the end. Another well-known technique for improving on the transmission loss of a single screen is to have a double screen, so a double skin partition. Now, above a certain frequency, the sound, the transmission loss in decibels simply add. So if you have two screens, the first one has a transmission loss of R1, the second one has a transmission loss of R2. The combined transmission loss R is simply R1 plus R2. And so if you have, say, 30 dB of reduction from the first one, and 30 dB of reduction from the second one, you get 60 decibels from the combined effect of having two together. And that only occurs at above this kind of critical frequency, F0, defined here in terms of the mass surface densities, mu1 and mu2. Okay, so I think I'm just going to finish off now talking about the effect of plate thickness. Now, this is very, very important, because if you're designing a panel on a structure to reduce sound, now there are two effects going on. One is that you're blocking the transmission of sound, but you're also exciting that panel to radiate sound. So as you increase the thickness of a plate, something bad happens, and the thing that bad happens is that it becomes a much more efficient radiator of sound. But the good thing that happens is that the transmission loss improves. So you've got to be very, very careful when you're designing these panels, because you might think you're blocking more effectively the transmission, but you're also making these panels more efficient as radiators. So when they're excited, they radiate more efficiently as a source of sound. So I think I've probably more than used up my time, so I apologize for that. So I've left here some references on noise control if you're interested. So on that note, Mr. Chairman, I'd just like to thank you for listening and finish my talk.
Thank you, sir. Any question, one question or two questions from the students or faculty?
Yes, sir. Good afternoon, sir.
Again, your voice is not very clear.
Sir, good afternoon, sir. Yes, sir. One of the questions asked, hello?
Yes, please proceed, sir.
Sir, Dr. Joseph, sir.
Proceed, sir.
If you take, for example, a suspension system in a car, when it vibrates, it produces some noise. Mostly when the suspension becomes older and older, it produces more noise. What is the reason for that, sir? The basic principle behind that. It's a question asked by one student.
So you're saying as the suspension gets older?
When it gets older, it produces some squeezing noise. So what is the reason for that?
Well, I'm just guessing. It's probably what Mike was saying, that I'm guessing it becomes less effective as an isolator. And so you're transmitting vibration down into the structure. And then the whole thing, that the whole shell would be vibrating as a sound source, which is why it's very important to decouple it from the rest of the car. So I don't know if I understood your question clearly. Are you talking about the suspension getting older? Is that what you said?
Sir, another question, I'll go for it. Last question. How good is elliptical shapes with respect to reverberation?
With respect to vibration?
Reverberation, he has asked. REVERBATION.
Well, I mean, it's probably more of a question for Mike, but as I'm talking, I'm guessing they're probably quite bad because structures are less stiff, aren't they? I mean, if you have
he said reverberation, not
vibration. Correct.
Reverberation. Oh, so reverberation. Sorry. I mean, regular shaped rooms are very bad. I mean, so if it was elliptical or if it was a cube, so what people try to do in general is to design rooms with irregular geometry. Because if you have a very regular geometry, then you could have lots of modes with the same frequency. Because what you try to do is try to distribute the modal resonances across the frequency range. So you don't have this clumping. So if you have an elliptical shape, then you could have quite a few modes with the same frequency. And so that room will respond very strongly at those frequencies and then have a much weaker response away from that frequency.
Thank you, sir.
So you could argue that a kind of a sphere is a kind of an extreme case of an ellipse. You know,
Okay.
even have even more. That would even be worse because you have lots of modes at the same frequency. So I'm not sure if I've answered your question very, very well.
Understood, sir. A little bit.
Thank you.
Thank you so much, sir. So now I humbly request our principal, sir, to propose the vote of thanks formally for the guest. Please, sir. Principal, sir.
Thank you, sir. Thank you very much
Yes,
for your excellent session, sir. Really, it was well received by our students and faculty members. So once again, on behalf of our respected chairman, sir, all the members of the management and all of us, so we would like to thank you very much for your excellent session and accepting our invitation. So thank you, sir. Thank you. Thanks for arranging this such a very nice session, mechanical HOD sir and all the faculty members, and also thanks to all the students. Thank you. Thank you.
Thank you. Thank you, sir. Thank you.
Thank you very much indeed. It's been a
We'll meet in RMK once. Thank you.
I very much hope so.
Thank you. Thank you.
It's been a
Dr.
real pleasure.
Chandrasekharan is on Zoom, sir.
Oh, he has come. Okay. 1 minute, sir. Dr. K.C. sir has come.
No.
Sir, please. Please, they are
Hello?
here. Happy to see you.
No, I think I lost